Hello guys, I'm Janvi and I'm currently studying in Data Science and Artificial Intelligence, second year from IIT Roorkee. Today, my topic related to applied linear algebra is least square and minimum norm solutions for rectangular systems. Now let's delve into this. Firstly, let's discuss about the importance of this topic. Why do we need special methods for solving linear rectangular system of equations? Generally, for solving system of linear equations of type, say, x equal to y, where A is square matrix of order n into n, that is order n, we simply get x by applying inverse of A on both sides, that is x equal to A inverse y, where A is a square matrix. What if the system is rectangular? That is, A is not square matrix, A is a rectangular matrix. That is, its order of m into n, where m is not equal to n. Then we know that inverse doesn't exist for non-square matrices. Then how to solve for x then? We have special methods to solve for x in that case. Also, we came to know that m is not equal to, what if m not equal to n? That is, either m must be less than n, which means that number of equations we have is less than number of variables we need to determine. Then the system is said to be underdetermined because we have less number of equations compared to number of unknowns to be solved. And what if m greater than n? That is, we have more number of equations than the variables. Then the system is said to be overdetermined or redundant. Let's see the methods we solve. So firstly, let's see what are the methods for solving underdetermined system of equations. There are three methods. The first one is generalized minimum norm solution. For solving underdetermined system of equations, we use the general method is by minimizing the norm. Say we need to solve for x. So say by norm I mean the magnitude of x. Either minimizing the magnitude of x or magnitude of x square, both mean the same. So the first method is minimizing that norm. And the second method is, even the second method is same of minimizing the norm, but this time we'll just be minimizing it with the help of Lagrange multipliers. That is by applying Lagrangian, and with that process we solve it. We'll see about it more. And the third method is relation to regularized least squares. By these three methods, we'll be solving the underdetermined system of equations. Firstly, let us see how to solve using the least norm solution method. Let's assume A is of full rank. That's its rank is M, where M is its number of rows. So we can say that A into A transpose is invertible. One particular solution of X in this case is X dash equal to A transpose into A transpose whole inverse into Y. This X dash equal to this thing is said to be pseudo inverse. So X dash equal to A pseudo inverse of Y in A pseudo inverse into Y. We can't just directly write x equal to A inverse Y since A inverse doesn't exist. So we can write x dash equal to A pseudo inverse of Y. This A pseudo inverse value is this, which is somehow proved and is generally called Moore-Penrose pseudo inverse. And here x dash is solution of y equal to ax. That minimizes the norm of x. That is, x dash is solution of optimization problem, which minimizes norm of x subject to x equal to y. That is, here x equal to y is the constraint. We need to minimize x given x equal to y. This is the meaning of this statement. So next, so now let's see the orthogonal point of view of this problem we discussed till now. This is the x and y axis, and let's assume two lines. This line consists of all x such that ax equal to 0. That is, this line consists of the region of null of A, null space of A. And let this be the line consisting of all x such that ax equal to y. We know that ax dash equal to y. The x dash we have seen before. And on this line, let us assume this is some random x. So this x equal to y. Y can be written as x dash. So a into x dash or x n, let's assume they both are same. So a into x minus x n equal to 0. And now let's just apply dot product of these two, or I mean some kind of A transpose into B kind of matrix. X minus Xin whole transpose into Xin. X minus Xin, we know that the value is A transpose since we saw from the previous slide. And now let's take this A into this and we'll see that A into X minus Xn transpose into all this. Since A into X minus Xin equal to 0, we get this as 0. It means that A transpose B equal to 0. It means that the both matrix, the both are, the dot product of them is 0. The dot product of the two matrices is 0. That is, they both are perpendicular to, the vectors are perpendicular to each other. That is, this is, we know that this is X bar and this is Xin. X minus Xin is this part. X minus Xin is perpendicular. So we can say that X minus Xin is perpendicular to Xin. It means that, so first, for finding mod x square, we can write it as Xin plus x minus Xin whole square. And this is A plus B whole square. So A square plus B square plus the angle between them, 2AB cos theta. The angle between them is cos theta. Cos 90 is 0. So we can remove that. And so Xin square plus x minus Xin whole square. Xin square plus some positive value. So this is greater than or equal to Xin square. So for any x, the norm of that x is always greater than or equal to Xin square. So since this is the shortest distance and Xin is the projection of origin onto this one, we can say that Xin has the smallest norm of any solution such that x equal to y. This is the second method, that is for solving x, the derivation via Lagrange multipliers. Firstly, we'll formulate a Lagrangian. That is, we'll write an equation of the form Lx lambda equal to x transpose x plus lambda of ax minus y whole transpose. Here, L is varying with respect to two parameters, x that we need to minimize and the lambda. Lambda is its own Lagrange parameter equal to x transpose x. This is called objective function or cost function, which we need to optimize. That is, minimize in this case. We need to minimize norm. That is mod x whole square. Mod x whole square equal to x transpose x. We know that. So we need to minimize this with plus lambda of ax minus y whole transpose. This ax minus y is said to be constraint, which has to be 0. That is ax equal to y. So this problem is basically minimizing x transpose x, where the constraint is ax minus y has to be 0. So here, by applying optimality conditions, that is, apply gradient for L with respect to x and also gradient of L with respect to lambda. Find the both and make them 0. That is, for the first case, x transpose x, the gradient with respect to x is 2x and then plus lambda of A transpose equal to 0. We can easily get this. And then also with respect to lambda, this will be 0 and this will be ax minus y equal to 0. So from the first equation, we will be getting x equal to minus A transpose lambda by 2. And putting this in this, we'll be getting A into x. What is x? Minus A transpose lambda by 2 equal to y. So from this, we can know that A into A transpose is invertible. That is, since A is full rank matrix. So A into A transpose minus by 2 lambda equal to y. So we can write lambda as 2 into minus 2 into A transpose whole inverse. We can take the inverse since it is invertible. So lambda equal to minus 2 into A into A transpose whole inverse y. So finally, putting this back in this, we'll be getting x equal to minus A transpose minus minus will get cancelled, 2 will get cancelled, A transpose into A transpose whole inverse y. So this is the solution. Which we got from by derivation via Lagrange multipliers, which we have seen in the previous slide. So this is how we derive. The third method is by relation to regularized least squares. That is, we know that least squares problem with here we'll be using the approach of Tikhonov regularization. That is to minimize half x minus b whole square plus eta square by 2 into mod x square. Mod x square is the norm which needs to be minimized, where eta is some Tikhonov regularization parameter. And then half x minus b whole square, where x minus b is a residual and which we need to make to 0. That is, we need to minimize this whole thing. So if we want to see into the proof, it will be like half x minus b whole square. We'll be writing x minus b whole square as x minus b whole transpose into x minus b plus eta square by 2 into x square. When we simplify this, we'll get like x transpose A transpose minus B transpose into x minus B. That is x transpose into A transpose AX, x transpose into A transpose AX minus x transpose A transpose B minus B transpose AX. If you can say, we can observe that let x transpose A transpose B be some k, then k transpose will be B transpose AX. So k plus k transpose, I mean similar. So we can write them like 2 of x transpose A transpose B. And then plus B into B transpose plus eta square by 2 x square. We need to minimize this. So we'll find the gradient of this with respect to x. Then we'll get like A transpose AX by partial derivative with respect to x minus 2 A transpose B. This will be 0 and this will be eta square by 2 into 2x equals to 0. So we'll get A transpose A plus eta square x, that is A transpose A plus eta square x plus eta square I into whole x equal to 2 A transpose B equals to 2 A transpose B. Wait. X transpose A transpose X. When we derive this, we'll be getting X transpose X. It is 2x, right? Derivative. And for this, it will be eta square by 2 into 2x. So eta square x. Okay, whatever. We'll be getting like this. Here the 2, and we'll get cancelled. We'll get A transpose A plus eta square I x equal to A transpose B. So now x can be written as A transpose A plus eta square I. This is invertible. So x equal to A transpose A plus eta square I whole inverse into A transpose B. This is what we can see here. X equal to A transpose A plus eta square I inverse A transpose B. So x is written as x eta since it's eta. Also now we can observe that observe what happens if eta tends to 0. If eta tends to 0, then x will tends to x transpose. Since C put theta is 0, then you will get A transpose A whole inverse into A transpose B. Since we didn't discuss the overdetermined solution, overdetermined system of equations yet, but in overdetermined system of equations, since underdetermined, we have x equal to A transpose in this way. I mean, not this. We have the pseudo inverse as A transpose into A into A transpose whole inverse B. Whole inverse B, right? X equal to. But in overdetermined, we'll have the we'll see it later. But just note that we'll have the pseudo inverse as A transpose A whole inverse A transpose. So we got x equal to A transpose A whole inverse A transpose B. Means that x extended to x eta. That is regularized solution converges to least norm solution. The regularized solution when eta tends to 0 converted to least norm solution. Similarly, with regularized normal equations, and there are this other set of equations R equal to x minus b, where R is the residual and A transpose R plus eta square equal to eta square x equal to 0. If we substitute these both, I mean, if we manipulate these both and solve, you will get x equal to A transpose we'll get this. Like see, there is this R, right? Put this R over here. And then you will get the equation for x, A transpose A x minus A transpose B plus eta square x. You can see it. You can actually see it. We will get x equal to this, the former thing. So just by playing with the set of equations we have, this one set of equations, and this is by minimizing this, we got two values of x. One is x equal to this and one is this. The former one is used for overdetermined system and the latter one is used for underdetermined system. When is eta tends to 0, this is used for overdetermined and this is used for underdetermined. So this is one other method for solving for relation to for solving for x. In the previous 3 methods, we have seen the 3 methods how to solve underdetermined systems. Now we will be seeing how to solve overdetermined system. What is an overdetermined system? Same, some matrix of Ax equal to B, where A is of order m into n, where m is greater than n. M represent number of equations and n represent number of equations to be solved, and n represent number of unknowns we have. Generally, if we have the same number of unknowns as that of equations, then you can solve it. But what if there are more number of equations? As the name suggests, the system is just overdetermined. You mostly come across this case in some ML applications where it includes data fitting. Say we have something like this. We find the training data set and like this. You need to fit this. Actually, this example seems to be slight easy, but generally you have more complicated methods. When you fit this, when you try to fit this using like this, then we generally use multiple regression for these models, and you will be getting something like y1 equal to a1 x1 plus so on, a2 x2 plus so on, an xn, where all these a's are parameters and x1 x2 xn or so on, or all the features, that's x1 x2 so on xn are the features, and you will get y1 y2, these are the result. During multiple regression, as actually I already said, and then you'll also get y2 equal to b1 x1. And since we know in ML, we'll be writing, we will need to find the relation between y and every input variable that is feature x. We need to find the equations. So we need to find the relation, then we'll be having equations like b2 x2 plus so on bn xn. And this like this we'll be having let x this, and you'll be having ym. When you write this, you will get a1 a2 so on an, this equal to y1 y2 comes so on ym. So you will be having m rows and n columns, where m is greater than n. Generally, say for example m is 10 and n is 4, you'll be having more number of equations, and if more number of equations than the number of parameters, then you'll need to find the almost near relation between them. In that case, okay, whatever. In that case, you will be using the overdetermined, you will be having the overdetermined system. And this generalized, the methods are the generalized least squares method, or the pure factorization for least squares, and SVD for least squares. We know SVD is singular value decomposition. These are the three methods we'll be using for solving an overdetermined system. Okay, let's see our first method for solving the overdetermined system. The first method is generalized least squares method. Here, the approach to approximately solve y equal to x. We need to solve y equal to x by defining residual or error. We generally take r, say r equal to ax minus y. If ax equal to y, then this r will be 0, or no, or else you will be getting this error. So this is considered as residual. You need to minimize this residual. So find x equal to x dash that minimizes r square. Generally, the residual you will be, since we know that you will be taking minimizing r and minimizing r square are both almost same. Okay, x dash is called least squares solution of y equal to ax. You need to find x dash such that a mod of ax minus y, the norm of ax minus y whole square is minimized. That x dash is said to be least squares solution of this. So how to solve for that? By minimizing r transpose r. You need to minimize this r square. R square is r transpose r. That is x minus y whole transpose x minus y. You will be getting x transpose a transpose minus y transpose into x minus y. So by multiplying on both sides, x transpose ax minus, since the both are the transpose of each other, they are the same, and minus 2y transpose x plus y transpose y. And now for minimizing this with respect to x, since the only variable is here is x, we need to set gradient with respect to x is 0. So applying partial derivative with respect to x, you'll get a transpose a, and for this you'll get 2x minus 2y transpose a, or you can write y transpose a or a transpose y plus y transpose y, this will be 0. So you get 2a transpose x minus 2a transpose y equal to 0. So a transpose x equal to a transpose y. Since a transpose a is invertible, you will just invert it. You will get x equal to a transpose a whole inverse into a transpose y. So you got the x. This is called the least squares method. And this x is called the least squares solution of y equal to x. In the previous slide, we have seen how to solve for x equal to y using the least squares method. Also, I want you to notice that for solving x equal to y in an underdetermined situation, you used minimum norm solution. That is, you minimized the norm, the mod x whole square, you minimize the norm. But here you are minimizing the least squares, that is mod x minus y whole square. That is, you are minimizing the residual. I need you to notice that in underdetermined system, you minimize the norm, And here you are minimizing the residual. Okay. The next, pure factorization. This is the next method, pure factorization for least squares. This is used for solving overdetermined system. In this case, you will just break up A into Q into A equal to Q into R, where Q will be an M into M orthogonal matrix and R will be an M into N matrix. So Q into R will be M into N, where since A is M into N, whose subdiagonal elements are all zeros. Look, R. R is like this, something like this. So R is of the form R1 comma 0, where R1 is this, and then you'll have all these zeros. And also notice the diagonal entries can never be 0. Given an given an M into N matrix of full rank, we can apply N householder transformations to 0. So householder transformations, you will learn more about it in Gram-Schmidt orthogonalization method. And generally, by applying N householder transformations, look, this is A, and you apply h1 for it. I mean, you pre-multiply it by h1, and then you pre-multiply it by h2. You will keep on pre-multiplying it with h1, h2, so on, hn minus 1, hn, till you get it in the form of R, where R is of the form R1 comma 0, till you get it the form of the matrix whose subdiagonal entries are all 0. You will be doing this. And once you get it, then you will, then also note that let all this multiplication of this hn minus 1, so on h1 equal to q transpose. Split it into two, q1 transpose, q2 transpose. Observe that you are going to do something with this r1 0, q1 transpose, q2. That's why you did split. Where q1 transpose is an n into m matrix consisting of, since you can notice that q1 transpose, so it will be transpose. It is an n into m matrix consisting of first n rows of qt. Q transpose, that is Q transpose. First Q transpose, you will be having first n rows. N into m, right? N rows, m columns, you'll be having first n rows. Since Q trans and also m, since m greater than n, you'll be having first n rows of total m rows. Since Q transpose A equal to R. Look, Q transpose A equal to R. And also, since Q is an orthogonal matrix, that is Q into Q transpose equal to I. So Q into Q transpose, by applying by pre-multiplying by Q on both sides, you will be getting Q into Q transpose A equal to QR. You will be getting A equal to QR. See, A equal to QR. This is the main objective behind this. A equal to QR equal to Q1, Q2, R1, 0. Let's since this just Q equal to Q1, Q2, and R is of the form R1, 0. So you get it like Q1, R1. Now let C equal to Q transpose B. You got this Q transpose, right? Q transpose into B. Here B is nothing like, but we are not solving for y equal to x. We are solving for x equal to b. Let's assume y equal to b. Then let's C equal to Q transpose B. That is Q1 transpose B, Q2 transpose B. Let Q1 transpose B is C1, Q2 transpose B is C2. Now I want you to observe that we have A equal to QR, and you have all this A equal to R. The normal equations can be written in the form R1 transpose Q1 transpose Q1 Rx equal to look, you generally write it as A x equal to B, right? So A is like R1 transpose Q1 transpose Q1 R1. Q1 transpose Q1 will be I, and you will be left with R1 transpose R1 and equal to R1 transpose Q1 B. Since Q1 transpose Q1 equal to I, these are the normal equations. And R1 transpose is non-singular. It is non-singular, so just don't inverse it. You will be getting R1 transpose R1 x equal to R1 transpose Q1 transpose B. Q1 transpose B is C1. So R1 x, so this R1 transpose don't conjugate, R1 x equal to Q1 transpose B. So that is the solution you will get. R1 x equal to Q1 transpose B, where Q1 transpose B equal to C1. So the equation gets simplified into R1 x equal to C1. So look, it used to be of the form Ax equal to B. You just simply did H1, H2, did Hn on, that is Q transpose on both sides. You got something of order X equal to B, right? You got something of this format, and then you Q transpose on both sides. You won't, that will be cancelled, and you'll get R1 X, that won't be cancelled, whatever. R1, you will get something of the form R1 X equal to C1. Now you know R1, and also you know C1, since C1 is Q1 transpose B. By back substituting R1 X equal to C1, you will get X. Also note that R1 and C1 both are of same order here. So just R1x equal to C1. C1 is Q1 transpose B. You got something like this, where R1, okay, you know that R1 is something, okay. R1x equal to Q1 transpose B. So the x is the least square solution of this. So by solving for x by back substituting, you will be getting the unique least square solution. So this is the third method for solving the overdetermined system. There is SVD for linear squares. SVD is singular value decomposition. SVD can be used to construct a generalized inverse of A. Here A is a non-singular M into N matrix with singular value decomposition. You know that you will decompose A into U sigma V transpose, where A is of order M into N, U is of order M into N, sigma M into M, sigma is of order M into N, and V transpose is of order N into N. Then A is this decomposition, and then the inverse A inverse is said to be this V sigma inverse U transpose. The proof of this one is like beyond the scope of what we discussed till now. It is actually verified and proved by some Penrose 4 equations or something. So let's not discuss that. Let's keep it for now. Let sigma be M into N of form. Sigma is M into N of form. Sigma 1 0 0 0. Sigma 1 is all these mu1, sigma 1, sigma 2, so on, sigma r. These are all the eigenvalues. These are all the eigenvalues of the matrix sigma. Then A transpose is given by the A pseudo inverse given by V sigma pseudo inverse U transpose. First, you will decompose A into U sigma V transpose. You will be getting U sigma and V all them, and then you will write A inverse as V, this V, and this sigma transpose. What is the sigma inverse? You can observe that sigma inverse 0 0. Instead of writing all the sigma 1, sigma 2, so on, sigma r, you will be writing 1 by sigma 1, sigma 2, so sigma r. So you will be getting this, you will be getting this, and you will be getting this. So you can write A inverse of this form. Also note that since this is of N into N form order, this is of N into M, and this is of M into M. So you will get A inverse is of N into M. In this way, from this SVD for linear squares, you will be finding the A inverse. So my topic discussion for today ends here, and I want to specially mention the resources W260 Stanford Intro to Linear Dynamic Systems and the Leon SG Linear Algebra with Applications 8th edition Pearson book. This book is really so good. And I also want to mention that the topic we discussed today has several applications. It is generally extended to Murray-Penrose pseudo-inverse, and then this thing is used in applications for signal processing and many such like that. So today my discussion ends here. Thank you. Thank you everyone for letting me do this.